Let's look at the Lewis structure for ozone. Ozone is 3 oxygen atoms bonded together in a molecule. So 3 oxygen atoms, there's really only one way to put them together. They must be in a line. So oxygen, oxygen, oxygen. How many valence electrons in O3? 18, right? So we've got 2, 4 from the bonds. 6, 8, 10, 12, 14, 16, 18. There's my 18 valence electrons. The oxygen on the end over here doesn't have an octet, so that's not okay. What do? We need to make a double bond. So this guy needs a double bond, and so I'm not going to use one of his lone pairs because he's already short. I'm going to use a lone pair from this atom because this atom has an octet. When I take a lone pair from an atom that has an octet, it still has an octet because it's sharing, and shared electrons count for both. So I'm going to take that lone pair up there, and I'm going to move it in here as a bonding pair. I still have 18 electrons, but now I have octets for everybody. Everybody okay with that?
Does it matter how we draw it? I think someone asked this earlier, but if I have it like in a triangle form, is that pretty much the same thing?
That's an excellent question. Can I draw it in a triangle? That is not the same thing.
Well, not like fully closed, but without one of the...
Oh, like just bent? Like that?
Yeah.
Yeah, you can draw it like that. That would be equivalent. So you could draw it like this. And that's just all twisted up. It is the same thing. So when I think about this molecule, think of it as a 3-dimensional object that you could either move around or you could move around it and look at it from different sides. When we draw this, so these atoms here, they're all oxygen, but they are different atoms of oxygen. So think of these as being a triplet, set of triplets, right? So there's Johnny and Bobby and Joey. I don't know, three little boys, right? And if you think about these electrons maybe as being cookies, and this guy gets 6 cookies to himself and shares 2 cookies with the guy in the middle. The guy in the middle is sharing cookies with boys on each side. He's sharing 2 pairs of cookies over here. He only has one set of cookies to himself. Is this kid going to be okay with that? No. They don't have exactly the same situation, right? They're both oxygens, but they are individuals as well. And the oxygen over here is thinking, why do I have to share here? And that guy on the other side doesn't. Well, why indeed? Why did I put the double bond on the right side instead of on the left side? There's no reason. I just happened to do it that way. It'd be interesting to go back through the lecture videos. I've done this lecture many, many times and see how many times does it end up being on the right the first time. But nobody's that interested to spend all that time, because that'd be dumb. Okay, so what if we drew it the other way and put the double bond here? And there's a lone pair there, and a lone pair, and then this guy. Now, you could argue that, well, this one is just that one twisted around. But if you give these names, let's just give them numbers. That doesn't work. 1, 2, 3, and this is 1, 2, and 3. Are these the same structure for 1 and 3. Over here, 3 has 2 bonds, and in this one, 3 has 1 bond. But you said you could do stuff like this. Well, yeah, you can. Oops. So 1, 2, 3. So this is equivalent to which of these? This one. So these are the same. Here, oxygen number 3 has 3 lone pairs and a single bond. Here, oxygen number 3 has 3 lone pairs and a single bond. In this one, oxygen 3 has 2 lone pairs and a double bond. That's not the same. Okay? So we can draw it this way, we can draw it that way. They are different. Which one is correct? Both. Yes, that's a trick question. They are both correct. And neither is correct. How's that? They're both correct and neither is correct. So what actually happens is the molecule exists as an average of these 2 Lewis structures. It doesn't go back and forth between the 2. It isn't this one sometimes and that one other times. It's actually an average, a combination of the 2. Lewis structures, Lewis theory doesn't deal with this very well. The best we can do is to put a double-headed arrow between these 2 equivalent structures. We say that these are resonance structures. Resonance always suggested to me that it was vibrating or vacillating back and forth between the 2. That's not what it's doing. It is an average. But we would deal with it this way. So we can have a 2 or more resonance structures whenever you have a situation like this where you have to give a double bond and you're choosing between 2 very equivalent situations. So let's remember what we had to start with. Let's see, 2, 4, 6, 8, 10, 12, 14. 16. And then we've got 2 more electrons. Well, we can put it over here, or we could put that lone pair over there and put the double bond over here. The double bond is between 2 oxygens regardless, right? They're equivalent. And that's the setup for a resonance structure. So the actual structure is a combination of the 2. So here we've got the 2 Lewis structures. It's a combination of the 2. Instead of ozone having a structure where there's a double bond and a single bond, we know from observing an ozone molecule that what it actually has is 2 equivalent bonds. Those bonds are the same. They can't be single or double, they're in between. So you could think of it kind of as a 1.5 bond. And again, Lewis theory doesn't deal with that very well. But we know from observations that that is what it is. It has identical bonds between the oxygens, which does seem more fair, right? And just to help you understand that it's not going back and forth, think about some dogs. Okay, so here we've got a German Shepherd, and that looks like it might be a white golden retriever, and they have puppies. And one of the puppies comes out looking like this. So this dog has some characteristics of the father and of the mother. But does this dog some days look like a German Shepherd and some days look like a retriever? No, it always looks the same, right? It's a hybrid, a combination of the 2. I told you on Monday that, Dr. K and I have a triple bond of 6 children. So he is of Japanese descent and I am of Swedish descent. And so, our coloring at the very least is very different. And so our children, what do you think they look like? Well, they're a combination, right? They look almost the same as each other, but none of them looks just like me. None of them looks just like him. They're a combination, right? I think they're a combination of all the good things about both of us. But So in the Lewis structures, we say the electrons are localized. We have to choose, is the electron associated with this atom or with that atom? It's localized. But in nature, electrons are often delocalized. They're actually spread out over the entire molecule. That results in a lowering of potential energy, and that lowering is called resonance stabilization. Any questions? Okay, so let's do nitrite ion. And it says include resonance structures. So that's a clue that there's going to be resonance structures. Okay, so we've got 2 oxygens and a nitrogen. We have to figure out how to put them together. Back on that slide with directions, it says that hydrogen is terminal, and often the more electronegative elements are terminal. What's more electronegative, oxygen or nitrogen? Oxygen. It's closer to fluorine on the periodic table. So the oxygens are probably going to be on the outside, and the nitrogens are probably going to be on the inside. So we'll start out that way. Nitrogen here, an oxygen on one side, an oxygen on the other side. And so we've got a nitrogen with 5 valence electrons, and we've got 2 oxygens. They each have 6 valence electrons. And what do I do with that -1? I add an electron to give it the negative charge. So 18. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18. Ran out of electrons, ran out of dots, but the nitrogen doesn't have an octet. So that's not okay. So we have to make a double bond. Should I put it on the left or on the right? Does it matter? It really doesn't matter, right? We just have to pick one. We'll put it on the left this time. So I'm going to take this lone pair and share it between the nitrogen and the oxygen. So I still have 18 electrons represented, but now everybody has an octet. And I need to put brackets and a negative on the outside. So I had to choose sort of randomly, do I put the double bond on the left or the right? That means that there's another resonance structure where I make the other choice. So I had this. And I had to choose where to put the double bond. I'm going to make the other choice. I'm going to put the double bond over here. So I'm going to take one of the lone pairs from that oxygen and share it with the nitrogen. That also has a -1 charge. And so those are the 2 different options. And they are resonance structures, and so we put a double-headed arrow between them to indicate that. The actual structure is a hybrid, an average of the 2. So you look at bond lengths and things, and you find out that actually this nitrogen-oxygen bond is identical to this nitrogen-oxygen bond. But Lewis theory doesn't give us a way to show that. Any questions? Well, sometimes we can come up with different ways of drawing a Lewis structure that don't really fit the pattern of a resonance structure. It's not just a matter of moving a double bond from this oxygen to that oxygen or something. It's actually doing something quite different. And so then how do we decide which is the best one? And we use something called formal charges to do this. So formal charges are fictitious charges that we assign to each atom. This is just a made-up thing to help us predict the correct structure. We ignore electronegativity when we do this. The way the book explains this, if it works for you, great. They say that the formal charge is equal to the number of valence electrons that the atom has by itself, and then you subtract the number of non-bonding electrons, the lone pairs, and half of the bonding electrons. So that's all fine, and that actually works. I find that difficult to explain to students and difficult for students to remember. So let me just show you how this works. Well, let's just make up an example. Let's just use one of those that we did just now, the nitrite ion, and see how we would assess formal charges. So the way I think of this is, so we've got these three atoms, and they came together, and let's say they maybe made a corporation, three business partners, and they're pooling their resources, right? And now they're disagreeing or whatever, and they're going to break up the business. I used to talk about divorce, but usually it's not just two people, and so a divorce between three people doesn't work out very well. So that's why I moved to the business. So we have business, three individuals, and now they're breaking up the business. They're each going to just cut their losses and leave. We're going to try to divide things equally. And so what they do is they say, well, we're just going to cut all the bonds in half, and you take half of it, and I'll take half of it. So to count the formal charge for this oxygen, what I'm going to do is I'm going to think about, well, how many valence electrons does oxygen have when it's by itself? How many did it bring into the corporation? 6. Right? So oxygen as an atom had 6. It came into the corporation, and now when it's leaving, how many does it take with it? 7. So 2, 4, 6, and half of that bond. Right? Because the bonds have an electron at each end. So sometimes drawing those in can help. So that oxygen is leaving with 7. What's 6 minus 7? -1. That is the formal charge on the oxygen. Let's look at this nitrogen. How many valence electrons does nitrogen have by itself? How many did it bring into the business? 5. How many is it leaving with when we break this up? 5. 5 minus 5 is 0. The formal charge on this nitrogen is 0. We don't usually write 0 formal charges, but I'm just going to do it here. What about the oxygen over here? Brought 6, because that's what oxygen has, and it's leaving with 6, right? 6 minus 6 is 0. So that has a 0 formal charge. That makes a lot more sense to me than this business of subtracting this and that and the other thing. But this does work, okay? So what we'll see in the next slide, some rules about formal charges, is if we take the formal charges for the 3 atoms in this molecule and add them up, they will equal the overall charge on the molecular ion. So -1, 0, and 0 adds up to -1. If you have a neutral molecule, all the formal charges will add up to 0. So let's look at those rules. So the sum of all formal charges in a neutral molecule must be 0. The sum of the formal charges in an ion equals the charge on the ion. Small or 0 formal charges are better than large ones. So the best Lewis structure will have the lowest formal charges that we can have. So when we look back at this one, is there a way we could rearrange these so that we could have lower formal charges? No. There's got to be one with a formal charge because there's a charge on this. It's an ion. We could move things around and have the -1 end up over here or in the middle, but we can't get them any lower. Sometimes you draw something, and yeah, by shifting electrons around, you can make it better. Here's another thing. How many bonds did I tell you that nitrogen likes to have? 3. How many bonds does this nitrogen have? 3. And its formal charge is 0. Oxygen likes to have how many bonds? 2. This oxygen has 2 bonds. Its formal charge is 0. This oxygen only has 1 bond. It has a non-zero formal charge. So if those elements have the predicted number of bonds, they're going to have a 0 formal charge. So that can kind of save you some time when you're making Lewis structures. When formal charge cannot be avoided, negative formal charge should reside on the most electronegative atom. So this is another of the reasons why we need to be able to predict electronegativity from the periodic table. You don't need to know what the actual electronegativity is. You just need to be able to say, well, this one's more electronegative than this other one. And so in this structure here, we put oxygens on the outside because they were more electronegative. And then we end up with the oxygen having the negative. And so that should make sense because more electronegative means more attractive to electrons, right? So if we've got an extra little boy thrown into this relationship here of little boys playing at different houses, he's going to go hang out at the house that's more attractive to little boys. The extra electron is going to be at the atom that's more electronegative. Okay, so let's look at hydrogen cyanide or hydrocyanic acid. And we can draw 2 different structures. There's structure A and structure B. So this one has carbon in the middle and nitrogen on the outside. This one has nitrogen in the middle and carbon on the outside. And we can predict which of these is better by looking at formal charges. So they've got it all listed out there, but let's just go over how that happens. So let's do structure A over here. So that's structure A and structure B. Before we do the formal charges, let's use the predicted number of bonds method. Carbon likes to have 4 bonds. Nitrogen likes to have 3 bonds. Which of these structures gives carbon and nitrogen the number of bonds they want? The first one. Here we've got carbon with 4 bonds, nitrogen with 3 bonds. I'm predicting that that's going to be the best one. So let's look at the formal charges. So we're going to take our structure and break it up. Cut the bonds in half. Just like you're going to split all is shared properly equally and you go on your way. Hydrogen's always going to have a 0 formal charge because it has 1 valence electron. It has to have 1 bond, and so it's always 0, so we can just ignore the hydrogen. Here's carbon. How many valence electrons did carbon bring into this molecule? 4. And how many is it leaving with? 4. 4 minus 4 is 0. So the formal charge on this one is 0. Nitrogen, it brings in how many? 5, and it leaves with 5. 0 formal charge. So this one has all 0 formal charges. That's awesome. Let's do this one over here. Again, cutting this in half. Nitrogen brings 5 and leaves with 4. So 5 minus 4 is a positive 1. Carbon brings 4 and leaves with 5 and is negative 1. The formal charges here, plus 1 and minus 1, add up to 0, as they have to if we're calculating these correctly. But then we look at these 2 structures and we say, well, this one has non-zero formal charges, and in this one, they're all 0. This is the better structure. Does that make sense? Are these resonance structures? No. There is more difference here than just the placement of a double or triple bond. How they're connected is different. You can't just shift electrons to one side or the other and get this. You have to break bonds and rearrange atoms. These are not resonance structures. Okay, assign formal charges to each atom in the 3 resonance forms of N2O. Nitrogen is central. Which resonance form is likely to contribute most to the correct structure? So oftentimes when we see something like this, where there's 2 nitrogens and an oxygen, a lot of molecules tend to be symmetrical, and so my gut instinct is to put oxygen in the middle and put the nitrogens on the outside. But that does violate the guideline of putting the more electronegative in the terminal position. And just to emphasize that, it tells us nitrogen is central. So we have to put nitrogen in the middle. So the first step is just a skeleton. So nitrogen's in the middle, and there's going to be a nitrogen on one side and an oxygen on the other side. We have 2 nitrogens. They each have 5 valence electrons, and 1 oxygen with 6. So there's a total of 16 valence electrons. So I've got 2, 4, 6, 8, 10, 12, 14, 16. So I gave octets to the guys on the outside, but that poor nitrogen in the middle only has 4 electrons. So we need to make some multiple bonds, right? So, well, let's take a lone pair from this nitrogen and move it to be shared with the other nitrogen. We're getting closer. But we still need more shared electrons, so let's take a lone pair from the oxygen and move it in here. Now we have octets for everybody. Could we draw it a different way? Yeah, I mean, it says there's 3 forms, so we got to, get a little creative and find out what those forms are. Oops. That's a good question. Could I draw oxygen on the left and nitrogen on the right? That would actually be the same as this. So when we looked at ozone, and we flipped it, we had a double bond with 1 oxygen and a single bond with the other oxygen, and those oxygens had different names, right? They were individuals, even though they look the same. Here we have nitrogen and oxygen. Those are actually 2 different elements, and so just turning it around is exactly the same. So we can't do that. But we do have choices about the second bond here. So let's see. We put 1 double bond in, and then we had this situation, right? Well, what if instead of taking this electron and making a double bond here, what if we took this pair of electrons and made a triple bond? That also works, right? So I'm going to take this lone pair and stick it in there. Do they each have octets? Yeah. Is this one different than that one? Yeah, because this one had 2 double bonds. This one has a triple and a single. Could we put the triple bond between the nitrogen and the oxygen instead? Sure. I mean, we're just drawing stuff, right? I'm going to put it down here because I didn't leave enough room. So I've got the same number of electrons, but now I've got a triple bond with the oxygen instead of the nitrogen, and then this nitrogen has its octet made up with lone pairs. So those are 3 different resonance forms. So what we've got here is the arrangement nitrogen, nitrogen, oxygen is the same for all 3, but we're just shifting around where we put the multiple bonds. So these are resonance structures, but one of these things is not like the others. Well, actually, none of them are really like each other. If this was an oxygen here and an oxygen there, then these would be equivalent resonance structures. But we're going to look at the formal charges and see that one of these is better than the others. So doing formal charges, you mentally, oops, wrong color, cut those bonds in half, and then look at how many the atom came with, how many it leaves with. Nitrogen, we know from its position in the periodic table, has 5 valence electrons. So it came in with 5, and how many is it leaving with? 6. So that's -1. The nitrogen in the middle also brought 5 in, and it's leaving with how many? 4. So that's a +1. And the oxygen over here brought 6 in, and it's leaving with 6. And so that's 0. Oxygen having an octet and 2 bonds, I actually don't have to do the math. It's going to be 0. Here, this nitrogen has 4 bonds, that has 2 bonds. They would each prefer to have 3 bonds, so those are going to be non-zero formal charges. So let's look at this one. Cut the bonds in half. How many bonds does this nitrogen have? It has 3 bonds, right? That's what nitrogen likes. If we calculate the formal charge, nitrogen brought 5 electrons in, and it's going to leave with 5. 0. This nitrogen has 4 bonds, 1, 2, 3 on one side and 1 over here. It brought 5 electrons in, it's leaving with 4, and so that's a formal charge of +1. And this oxygen brought 6 in, and here it's leaving with 7, so that's -1. So looking at these two structures, we see that we have -1, +1, and 0. Here, 0, +1, -1. The value of the numbers is the same, the magnitude. They're just in different places. But in both situations, they add up to 0, as they should. And then let's look at this guy over here, cutting him up. The nitrogen here brought 5 electrons and is leaving with how many? 7. So that's a formal charge of -2. The one in the middle, 5 minus 4 again. And the oxygen over here, 6 minus 5. So here, we've got -2, +1, and +1. Those formal charges are larger than for these two, right? The best one is the one with the lowest formal charges. We're asked to figure out which is likely to contribute most to the correct structure. Well, it's not going to be that one, because that's higher formal charges. That's not as good. Here we have the same formal charges, they're just in different places. We have a negative formal charge. The best one will give the negative formal charge to the more electronegative element, which is what, nitrogen or oxygen? Oxygen. Oxygen's more electronegative. This structure gives the negative formal charge to oxygen. And so that's our winner. Winner, winner, chicken dinner, right there. These are resonance forms, but they don't contribute equally. So if you look at my children, you will note very quickly that they did not draw equally from the two very diverse gene pools. My children have dark brown hair, dark brown eyes, and lovely brown skin that they just go out and look at the sun in the spring and they turn this beautiful golden brown color. I go out and look at the sun and I turn beet red, right? Blonde hair, green eyes. They look much more like my husband. He is a more stable resonance structure. He contributed more to the hybrid than I did. I did have contributions though. Any questions? Yeah.
Would that one be a better choice as well because it has a triple bond and nitrogen wants the triple bond?
That's a good question. Would this be better because nitrogen has a triple bond here? Yes and no. You can't really use that solely to tell you what's going to be happening. But this triple bond on the nitrogen lets me know that that nitrogen is going to have a zero formal charge. And so anytime I can move bonds around so that atoms have the desired number of bonds, I'm going to have lower formal charges. And so generally that's going to be better. The reason that this one is better, though, is because the negative formal charge is on the more electronegative element. Any other questions? Okay. Draw the Lewis structure, including resonance structures, for diazomethane, CH2N2. And we're told that carbon is central. For each resonance structure, assign formal charges to all atoms that have formal charge. So what that means is if it has a zero formal charge, we don't have to write that in. So we're told that the carbon is central. So we're going to put the carbon in the middle. And then we've got 2 hydrogens and 2 nitrogens. And so we'll just sort of start kind of randomly and say, well, what if they're all attached to the carbon? We'll put a hydrogen here, and a hydrogen here, and a nitrogen, and a nitrogen. And that's looking pretty good for the carbon, right? Because carbon likes 4 bonds, and it's got 4 bonds. So we'll start with that. We have to figure out how many valence electrons. So carbon has 4, and then we've got 2 hydrogens. They each have 1. And we have 2 nitrogens, and they each have 5. So 10 and 2 and 4 should be 16. So we got 2, 4, 6, 8, 10, 12, 14, 16. Not enough. We need multiple bonds. Where are we going to put multiple bonds here? Put a double bond between the carbon and the nitrogen? Can I do that? No, carbon already has an octet. It doesn't want 10. I'm kind of stuck, right? That tells me I put it together wrong. Did that on purpose. So back up. That didn't work. So let's try moving one of these hydrogens. I can't put a hydrogen on a hydrogen, but I could put the hydrogen on the nitrogen. So let's try that. Put the hydrogen over here. 2, 4, 6, 8, 10, 12, 14, 16. I'm still in that situation where I don't have enough electrons, right? But now I have a place where I can make a double bond, right? I could put a double bond between this carbon and the nitrogen, right? So let's do that. We'll take this one here and move it in there. Is that good? It was better. Carbon, okay, hydrogen's always fine. This carbon has an octet, that nitrogen has an octet, but this nitrogen does not. It only has 6. So we need to do more sharing. Is there a place I can make another multiple bond? No. If I make a multiple bond between this carbon and the nitrogen, then the carbon's got too many bonds. If I go between the carbon and this nitrogen and go for a triple bond, carbon still has too many bonds. I can't do anything with the hydrogens. So what does that tell me? I put them together wrong. Again. Oh wait, I wanted to keep that. Well, what else could we do? We could put this hydrogen on the nitrogen, see if that helps. Because we're told that carbon is central. So carbon is in the middle here. So 2, 4, 6, 8, 10, 12, 14, 16. Ran out of electrons again, so I need to make multiple bonds. So I'll take this lone pair and share it with the carbon. So now this nitrogen has an octet. This nitrogen has an octet, but the carbon doesn't. This time, though, I can take one of these and share it with the carbon. Now, does everybody have an octet there? Yes. It says including resonance structures. So I'm going to draw this out a little neater. So I've taken this structure and I've just straightened it out. Could we move those multiple bonds around? We've got 2 double bonds. We could have a triple bond and a single bond. So let's try that. Resonance structures are going to keep the same order of connection. But now let's put a triple bond over here and a single bond over there. I've got the same number of bonds. I'll have the same number of lone pairs. So that means I have to put 2 lone pairs on that nitrogen. What's the other resonance structure? Triple bond on the other side, right? So carbon, triple bond with this one, single bond with that one. These are both nitrogen atoms, but like twins, you talk to 2 identical twins and they may look the same, but if you talk to them, they'll say, no, I am an individual person. I am not my sister, right? So that's how nitrogen feels as well. So these last 2 that we drew, those are equivalent, right? The only difference is triple bond on one side, triple bond on the other side. This is a resonance structure, but it's a little different than these 2, right? So then we're supposed to assign formal charges. Carbon has 4 bonds in each of these. So in all of these, carbon has a 0 formal charge because it brought in 4 electrons and it's leaving with 4 because when we cut the 4 bonds, it'll have 4 electrons. So that's 0. The hydrogen's always 0. So let's look at the nitrogens. So here, this nitrogen has 3 bonds, and so we're thinking that's probably going to be a good thing, right? The nitrogen brought in 5 electrons, and it's leaving with, we got to split these 2. It's leaving with 5 electrons, right? Because it's got 1 from this bond, and 2, and 3, 4, 5. So that one's 0. And over here, this one's also 0, right? So that's probably our winner right there. In this one, this nitrogen brought in 5 electrons and leaves with 4. So that has a +1 formal charge. Over here, nitrogen brought in 5 and leaves with 6, and so that's a -1 formal charge. And it's reversed down here. So if we look at these two, we can't say that one of these is better than the other. They're equivalent. But this one has 0 formal charges for everybody, so that's the best one. There's a resonance between these three, but this one has more contribution to the overall structure. Any questions? Yeah. Okay. Uh-huh.
Is there a reason why you can't bond the nitrogen together?
That's a good question. So let's whoops, didn't mean to do that. Yeah, I made it go away. That's okay. What if we did, I think what you're asking is, what if we did this?
More so like demonstrated, or if I go to the and then it was negative to the also.
Like that? Like that?
Switching the image.
Going from left to right, we want hydrogen, carbon, nitrogen, hydrogen, and then under the carbon, another nitrogen.
So I don't know, last one you do, just switching like nitrogen and hydrogen.
Okay, so that is just a different. So something like that. Oops.
It was like the last one you do before you changed it, but where the nitrogen like two nitrogens are next to each other instead of the last one.
Pardon me?
Where the last one that you did before you changed it,
Mm-hmm.
where the nitrogens are next to each other rather than across from each other.
So just switch these two?
Yes.
Okay.
That's not the first one we did.
That's not gonna help us out at all.
I was wondering why you couldn't bond the nitrogens together in that form.
You mean and do like this?
In that form, you're aligned between the two nitrogens. Is that just like an illegal process that we can't do? No. It's different.
Like make a triangle out of
Like a
carbon,
diagonal line.
nitrogen.
Like making a triangle?
Yes.
Okay. Yeah, we can't do triangles.
Okay.
And let's try it. So, where's my pointer? Come on. 2, 4, 6, 8, 10, 12, 14, 16. Now what?
You not share another one between the nitrogens?
So do this. 1, 2, 3, 4, 1, 2, 3. I guess that does give us an octet. The thing is, that is a very small ring structure with just 3 atoms. It's possible to do that with carbons, but they're not happy about it. And so in this class, you're never going to see a triangle. You're not even going to see a square. You might see a pentagon or a hexagon, but what we'll learn is that there's geometry, 3-dimensional geometry associated with these atoms, and this would be very, very strained. This is, like you holding hands with somebody by sticking your head between your legs and your arms through, and you're walking around like that. It's just not comfortable, right? You're very twisted up. And so they're not going to do this. But you are correct. We can, in theory, draw a Lewis structure that way. Sorry it took so long.
You draw with that one too, right? With the carbon in the middle and nitrogen?
I think we tried that, didn't we? 1, 2, 3, 2, 4, 6, 8, 10, 12, 14. We have no place to put the. So let's try that again.
Can you do a double bond?
2, 4, 6, 8, 10, 12, 14. I can't put the last. Oh wait.
Yeah,
The
carbon and
carbon,
nitrogen.
2 double.
No, in the bottom, so it's out of, yeah, the nitrogen.
2, 4, 6, 8, 2.
Between carbon and nitrogen.
Double bond.
Double bond between carbon.
Like that?
But carbon is not like in the middle. It kind of is, but it kind of isn't.
Yeah, it kind of is, but it kind of isn't. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So we can draw that. What would the formal charges be? Does carbon have a formal charge there? No, it's got 4 bonds. How about this nitrogen? Comes with 5, leaves with 4, plus 1. And the other one has a -1. So we can draw that one, but yeah, that doesn't fit this. Carbon is central.
So both of those would still be Lewis structures?
This one is a valid Lewis structure. That one isn't, because I'm telling you, no ring around the rosy.
These would only be model kits, because if you couldn't put them on,
Yeah,
it wouldn't work.
we can play with the model kits, and you'll find out that there's no way you can make that with the model kit. And the model kit has the same geometry that the actual molecules will tend to do, and so if you can't make it with the model kit, it doesn't exist. Which is not a great scientific reason, but it helps us to understand. Any other questions?